You've probably seen AI-generated images online, from photorealistic portraits to fantastical landscapes. But have you ever wondered how these images are created? The answer might sound counterproductive. Imagine a photo gradually being corrupted by noise until it becomes indistinguishable static. Now imagine reversing that process, starting with pure static and gradually seeing a new photo emerge. That's how diffusion models work. They learn how to extract a coherent image from noise, and they do that by first adding noise to lots of images, in some cases, billions of them. The details of how this works are complex, but one way to think about it is to imagine a swimming pool filled with static noise instead of water. Now take a photo of a flower and drop it into the pool. As the photo sinks down, the data describing how the pixels are organized starts to dissolve and diffuses into the pool of static. As the photo dissolves, imagine keeping track of the difference between the noisy photo and the original one. Intricate shades of color might start to blend together, and individual petals might merge. You might just catch a glimpse of a green blob before all that's left is the noise. So you keep track of all those changes as they happen, noting the difference between the noisy photo and the original one. At the end of the process, all the information in the photo has fully diffused into the static. Now imagine doing that same thing for 1 billion or more images. Once you finish, you have all the information needed to go from static noise to noiseless images. Since you kept track of the differences between the noisy and original photos, we can take some static in the pool and predict how much noise we need to remove to produce a new photo. And if you also give the model a prompt to narrow down what you're looking for, it can use what it learned from diffusing all those other photos into the pool to create a new image that's different from anything it saw before. But this technique isn't just for creating art. What if we could apply the same principle to chemistry? Imagine designing new drugs or materials by gradually refining collections of atoms from a pool of static to form new molecules. Just like with images, we can add noise to the structure of a large collection of molecules, disrupting their bonds and properties. Then, the trained AI model can remove the noise to produce new molecules. Better yet, we can guide the newly forming molecule towards a new configuration with specific characteristics that are important to us. This process allows scientists to explore vast chemical spaces that were previously inaccessible, which paves the way for the discovery of new molecules with properties tailored for specific applications, like pharmaceuticals, sustainable materials, or even energy storage solutions. This technology is still in its early stages, but the potential is immense. Diffusion models could accelerate drug discovery by generating promising drug candidates. It could revolutionize material science by designing new materials with tailored properties. And it may even help us tackle environmental challenges by developing molecules for cleaning pollutants or capturing carbon. So diffusion models aren't just about creating images or generating molecules. They're about exploring the vast possibilities that lie within the noise of a trained model. By harnessing the power of randomness and guided refinement, we're watching the next scientific breakthroughs emerge from the noise, one molecule at a time.